What you're looking at right now is Metallica. Pretty good stuff there, yeah? Hey, what I have going on here is a virtual oscilloscope. You could look this thing up too. What you see that it's mapping out here is it's mapping out sound waves in a visual format that you can actually see and access here on this thing. You could play with this thing if you wanted to. Go to virtual oscilloscope and then click the input here. If you change the input to input live, it'll show on the little screen all of the sounds that it's hearing, which for us was Metallica and now is my voice. And with the lag, it probably just looks pretty random. But here's what I want you to notice, is that when you play music onto this thing, you're not getting nice smooth waves. No, you're getting kind of crazy kind of waves that are all kind of all over the place. Today what we're going to talk about is why these waves look the way they do and why some instruments sound different than other instruments. And how can you account for those kinds of things? Today, we're talking about the physics of music. You can do it, buddy. There we go. Oh, well, never mind. And wow, look, this is so embarrassing. I already have notes up here. What? No spoilers. Hey, while I erase these, there are 3 words up here that you do need to know about. Those 3 words are resonance, resonance frequencies, and standing waves. Please take a moment as I erase all of this work, which we're actually about to put up here in a little bit, but I'm going to explain it first. Can you please take a minute and explain to yourself those 3 terms: resonance, resonance frequencies, and standing waves. You'll need to understand all 3 before we take notes today on the physics of music. Hopefully, you're feeling pretty good about resonance, resonance frequencies, and standing waves because you're going to need to know all about them. You see, standing waves are pretty much the whole basis of how all musical instruments work, and standing waves rely on resonance frequencies, so you really need to feel pretty solid on these 2 topics. What we're going to be talking about today is how different instruments are made and why some instruments sound different than other ones, and then how once we have an instrument, we make different notes on that instrument. We're going to talk about 2 types of instruments today. We'll talk about string instruments, and we'll also talk about wind instruments. We'll start by talking about string instruments, and then we'll talk about wind instruments. And we're going to use string instruments as kind of our model for a lot of the concepts that we'll talk about today, especially with standing waves. But these same concepts apply to both string instruments and to wind instruments. Let's start by talking about a string instrument. Now, a string instrument, always, and wind instruments as well, they all rely on standing waves. Here's what happens. If I have a ukulele like this, and I play one of the strings like so, what I do is I set up a standing wave on this string right here. You can see it's attached to this end down here. It's attached to an end up here. You get a vibration that travels along this wave. That vibration vibrates back and forth. It interferes with itself on either ends with constructive and destructive interference, and you get a standing wave as a result. Now, that standing wave, if you were to ask what's the frequency of the standing wave that results on that string, the frequency of the standing wave is the resonance frequency of the string. If you remember how we talked about in our last video, we talked about resonance frequencies and how everything has a natural frequency that it likes to vibrate at. Well, this string on this ukulele is no exception. It has a favorite frequency that it likes to vibrate at. Its natural frequency or its resonance frequency. If you pull that string back, just like pulling back a little pendulum, and you let that thing go, it'll go back and forth and back and forth and back and forth and back and forth at its favorite frequency, at its resonance frequency. And that will result in a standing wave. Here's the idea. The idea is that resonance frequencies on strings result in standing waves. And if you pluck a string, it'll naturally resonate back and forth, or it'll naturally vibrate back and forth at its resonance frequency, and this will result in a standing wave on the string. Now, there are actually, truthfully, more than one resonance frequency that works for a string. Here's one way that you can get a resonance frequency that results in a standing wave. Say that you had a ukulele string that was tied down on both ends. So it was tied down here at the headboard, and it was also tied down here at the base. And you had this string. Oh, wow, that was not straight. Let's try again. That was resting at its equilibrium position between this point here where it's tied down and this point here where it's tied down. If I took the string and I pulled it back and I let it go, that string would then begin to oscillate. So the string would go up and down, and sometimes it would go up and end up like this. Other times it would go down and it would end up like this. Oh gosh, oh my. This is just embarrassing. Okay, sometimes it would go down and it would end up like this, and it would oscillate back and forth between these 2 points. Well, here you see that we have a standing wave that has a node right here, a node right here, and then oscillation between those 2 points. Well, this is what happens if you pull back on a string and it oscillates back and forth, but there's actually more than one resonance frequency that would create a standing wave on a string. You could also create a standing wave on a string that looks like this. Suppose that you had the same string, same length, but now you created a wave that looks something like this. Okay. This wave would also be a standing wave. You could imagine that you could have one node in the center, one place in the center of the string where the string isn't moving up and down that much. The ends are fixed, so they're stuck, so that gives you 1, 2, 3 nodes in total. Then you have these antinodes here, these regions where the string is bouncing up and down like crazy. This wouldn't just happen at any old frequency. No, you would have to find a very, very perfect frequency where this would happen. Same thing with this top one. This wouldn't just vibrate back and forth at any frequency. It would vibrate back and forth at its favorite frequency, at its resonance frequency. And this one, too, you would have to find a very, very specific frequency. It couldn't be at any frequency. You would have to get the frequency that perfectly fits one wavelength worth of wave onto the string. Do you see how this one wave has an up part and a down part? It's one wavelength long. You would have to find the perfect frequency that fits one wavelength worth of wave on the string. You could also create another resonance frequency, and it would look something like this. It would look something like whoop, 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 like this. This resonance frequency would create a standing wave that has nodes here, a node here, another node on the end, and another node on the end. That's a total of 1, 2, 3, 4 nodes, and it would have 1, 2, 3 antinodes, like this. All of these would be resonance frequencies, but they would all create different standing waves. In fact, when you pluck a string, it actually plays not just one of these, but multiple of these. We'll explain that more in a second, but first, we're going to do some work labeling these different types of resonance frequencies, which create different types of standing waves. Let's go here. Oh, look, it's still my oscilloscope. Bye, oscilloscope. Peace out. Okay, go. Okay, well, yep, this is working so very well. If we go here to, not that one, actually. Wow, this is just so embarrassing. Oh my, look at my unpreparedness. Okay, right here, this is the one that I wanted to show you. It's only going to take like 5 years to load, but eventually it's going to be here. Don't even worry about it. It's on its way. We'll zoom in a little bit here so that you can see this slightly better. That is a little bit too much. Sorry, we got a lot of lag going on here, which makes it very hard to be precise. Okay. And, well, I feel like at the end of that, I did pretty much nothing. But that's okay. Here we are, and we're going to use it. It's going to be totally awesome. Okay, so here's the thing. You have for any, let's get our marker out. You have for any given wave, or for any given string, you have multiple frequencies that will act as resonance frequencies, but they'll just create different looking standing waves. This one right here is what we call the fundamental frequency. The fundamental frequency. And it creates a standing wave that looks like this. It has one node right here, one node right here, so that's 2 nodes. It has one section right here that's oscillating up and down. Whoop-a-doop. So it has one antinode. And the length of this thing, if you look, the length of a wave is an up and a down. An up and a down together creates one wavelength. So this thing right here has only an up. It only has a half of a wavelength. It fits about a half of a wavelength on the string. This fundamental frequency occurs at a frequency that we call F naught or F0, and it just means the first frequency that's a resonance frequency. Now, this fundamental frequency sometimes gets called the first harmonic. But you can use these two terms interchangeably. You can either call it the fundamental frequency or you can call it the first harmonic. It's that frequency at which you get the first resonance frequency. It's that first standing wave with two nodes, one antinode, and a half a wavelength. The second harmonic, what we call the second harmonic, is the second possible resonance frequency for a string. And it happens when you get a string that looks like this. It's a standing wave, once again, and it doesn't just happen at any old frequency. It happens at a very specific frequency, but it gives you 1, 2, 3 nodes here. So we have, I'll write this off to the side. We got 3 nodes. It gives you 1, 2 antinodes, and you can fit a total of 1 wavelength here on the string. Notice I have an up part and a down part. So it's 1 wavelength on the string. This second harmonic, I told you, occurs at a very specific frequency. The frequency that it occurs at is 2 times the fundamental frequency. So if we had a string that had a resonance frequency of 3 hertz, this second harmonic would occur when that string vibrates back and forth at a frequency of 6 hertz. At that frequency, you would get a standing wave that looks like this. But there are 2 terms that we can use to describe this. We can either call it the second harmonic, or we can also call it the first overtone. The first overtone. I'm going to run out of room here. Overtone, spelled like over and tone. The first overtone. We'll talk about why we call them overtones in a second. If we call this one the first harmonic, this one the second harmonic, you can bet we call this third resonance frequency the third harmonic. The third resonance frequency gets called the third harmonic, or sometimes it also gets called the second overtone. And this second overtone, this third harmonic, doesn't occur at just any old random frequency. It happens at 3 times the fundamental frequency. So for a string that has a fundamental frequency, its initial resonance frequency, its natural frequency is 3 hertz. The second harmonic would occur at 6 hertz. The third harmonic would occur at 9 hertz, and what you'd get is you'd get a standing wave that results when you vibrate it back and forth at 9 hertz that has 4 notes, 3 antinodes, 4 notes, 3 antinodes, and a total of 1 wavelength and a half a wavelength. So 1.5 wavelengths, or 3.5 lambda. I bet you at this point you could fill out all of the information for this guy right here. Can you write it down on your paper? I'll write it down up here. Did you say that this is the 4th harmonic or the 3rd overtone? And that it occurs at a frequency of 4 times the fundamental frequency? Did you say that it has 5 notes and 4 antinodes and it takes up 2 wavelengths on the string? Because that would all be correct. Now, all of these are resonance frequencies that would create standing waves on the string. So the question is, when I pull the string back on my ukulele, which one of these 4 does it choose? Or does it choose the 5th harmonic? That's the 4th overtone, which has a frequency of 5 times the fundamental frequency. Or does it choose the 6th harmonic or the 5th overtone, which has a frequency of 6 times the fundamental frequency? Which frequency is it going to choose? The correct answer is yes. It's probably going to choose multiple of them. And which multiple it's going to choose depends on the instrument. Hey, if I took this, oh wait, let's go out of my marker mode. If you need to, take a quick pause here. Make sure that you get all this written down because the marker's about to disappear. Bye, marker. If I took this ukulele here and I played a note on this ukulele like this one, and then I put this ukulele away and I took out instead a violin. And let's say that on my violin, I didn't even take out my bow. Let's say that I just plucked the exact same note on the violin. Oh, that's not the exact same note. Wow, that was embarrassing. The exact same note on the violin. Like that. And I told you, hey, close your eyes. Don't look at the camera. Don't look at the video. Just close your eyes and hear. Can you tell the difference between a ukulele note and a violin note, even if they're the exact same note? Odds are you would say, yeah, I can. I can tell the difference between the sound of a ukulele and the sound of a violin. They sound different, Miss Wilson. That's true. A violin and a ukulele do sound different than each other, even when they're playing the exact same note. And that's because the different harmonics that show up from a ukulele versus from a violin are totally different. Let me show you a picture here. If it'll load, then you can see it. Yes, here it is. Okay. Here I have 3 different instruments, a viola, a clarinet, and a tuning fork. Each one has its own, what we call, complex waveform. Here's what a complex waveform is. When you play a note on the viola or on the clarinet or on the ukulele, it doesn't actually just play one of these harmonics. It actually plays multiple at the same time. Now you say, Miss Wilson, how is that possible? How is it playing multiple harmonics at the same time? Well, let me see if I can draw you a picture that makes sense. Suppose that you had a ukulele that was playing and you played one note at the first harmonic, a fundamental frequency kind of note. What would happen is you would pull that string would vibrate back and forth, and it would oscillate back and forth like this, creating the first harmonic. But that's not all that it would do. Because when you pull it back and forth, it's not just going to go like this. What's really going to happen is that little mini waves are going to ride on top of the bigger wave. Imagine if, as this thing was moving back and forth, another wave was also riding on top of this wave here like this at the same time. And so imagine you had a second standing wave on top of the first standing wave. And those two waves were happening at the same time. Then imagine if on top of this last wave, you had a third wave that was going like this, that was riding on top of it. And so then you have not just one wave happening, not just two waves happening, but you have a wave riding on top of a wave, riding on top of a wave. Well, that would look very, very complicated. In fact, I'll just show you what it would look like if you had a wave riding on top of a wave. It would look something like this. You'd have something that looks like this. And this is so hard because of the lagginess. Something that looks like this. Hey, do you see how this is made up of two waves? There's one wave that's just going up and down like this. Up and down like this. But then there's another wave that's riding on top of that wave that's going up and down in a smaller way like this. It's a wave riding on top of a wave. If you could see what it looks like, okay, now I'm going to delete all my markers here, so bye markers. If you could see what it looks like, it would look kind of something like this. You'd have a little wave that's also tracing along the path of a bigger wave as it goes. And truly, I have no idea if you can see that clearly because of the lagginess of our software, but you get the general idea. It's a wave that's riding on top of another wave. Now, here's the thing. Let's go back to our picture of different instruments. Okay. Here we have our different instruments. Here's the truth, is that different instruments have different complex waveforms. They have different waves riding on top of each other. So here's what this one has. The viola has the first wave. It has that fundamental frequency, that one standing wave with one little antinode sort of situation, and it has that one. And then riding on top of that wave, it has a lot of the second harmonic. So the second harmonic is riding on top of the first harmonic. Then you have a little bit of the third harmonic riding on top of that, and then a small sprinkling of the fourth, the fifth, the sixth, and the ninth harmonic riding on top of that. That particular combination of harmonics gives you this particular complex waveform. And that is what a viola sounds like. A viola is the only instrument that has this exact combination of harmonics, this exact combination of notes, so that when you pluck a string on the viola, it'll play exactly these harmonics in exactly these proportions. No other instrument will do it the same way. If you look at a clarinet here has a lot of the third harmonic. It's mostly the third harmonic. Then it has a lot of the first harmonic, a little bit of the second harmonic, and a sprinkling of the fourth, the fifth, and the seventh. When you play a clarinet, it gives you a waveform, a complex waveform. Whoa, my marker just turned on. A complex waveform that looks something like this right here. That complex waveform is unique to a clarinet. No other clarinet has that particular combination of harmonics. So, here's how your brain can distinguish between violas and clarinets and ukuleles and tubas, is it can hear the difference in these resultant waveforms here. There's only one instrument in the world that only has one harmonic in its waveform. Okay, and it's the tuning fork. The tuning fork only plays one note. It only plays the first harmonic, and that's all, which makes it a very, very boring and uninteresting instrument. This is why we don't have tuning fork choirs, and nobody goes to see the tuning forks all play together, because it's not a very interesting sound to your brain. There's only one note to it, not a lot of uniqueness or interestingness going on, but it does make it very good for its purpose, which is tuning. It's only playing one note, so you can hold it next to your ear, you can hear that one note, and that one note is the note that you're supposed to play. Unlike the viola, which has multiple notes that it's playing at the same time, but some are just underlaying the other ones. or a clarinet, or a ukulele. Same thing. Every note is actually layers of multiple notes that are all kind of riding on top of each other to create this complex waveform. We call this complex waveform, or the sound that you hear, we talk about it as being the quality or richness of the tone. When you're talking about how one instrument sounds different than another one, when you're talking about this complex waveform here, you're talking about the quality of that tone or the richness of that tone. The only guy who has a pure tone, a very uncomplex and simple tone, is the tuning fork. Again, very uninteresting to listen to. So that's why one instrument sounds different than other instruments, is because of their complex waveforms. Now, let's take a look as to how string instruments and wind instruments actually work. We know how they sound different from each other. It's because of the ways that they have different complex waveforms. But what we're going to talk about now is how do you actually play an instrument to make the sounds that you want to sound. Now, here's the thing, is that if you had a ukulele like this one, but it only played one note, if it only had one resonance frequency here, and that was all that it could do, it could only play one sound, well, that would be a very boring and uninteresting instrument. So instead, we make our instruments so that our instruments can play at a variety of resonance frequencies. And the way that we do that is we build them in such a way that we can vary certain attributes of those strings. We'll talk first about how you can make different notes on a string instrument, and then we'll talk about how you can make different notes on a wind instrument. We'll start here with string instruments. And let's pull up a new drawing, shall we? Because we are quite full over here. Ba-doo-ba-doo. Loading. Do-ba-doo-boo. Loading. Okay, let's start by talking about string instruments first. Oh, I gotta slow down. I'm going way too fast. And this little thing will not be able to keep up with me. Okay, string instruments. There we go. Nice and slow. String instruments. Here are the various factors that impact the resonance frequency of a string. Before I write them down, you make a guess in your notes. Could you figure out the various factors that would impact the resonance frequency of a string? Here's the first one that I got. The length of the string. Here's how this works. If I want to change the note that I'm playing, one thing that I can do is I can change the length of the string. Now, the way that I change the length of the string is not that I take the string, I cut it off my ukulele, I shorten it up a little bit, and I reattach it on. No, that would be crazy, and that would break my ukulele. No, what I do instead is I change the length of the part of the string that's vibrating by moving my finger up and down the fret. You can hear here, it's a lower note. Then, as I shorten the length of the string, that note gradually becomes higher and higher pitched. This shows us that the frequency of a string, that resonance frequency, that fundamental frequency, is inversely proportional to the length of the string. As the length gets smaller, the frequency gets higher. As the length gets longer, the frequency gets lower. That's the first thing that matters. Let's talk about another thing that matters. Another thing that matters is the amount of tension in the string. The amount of tension in the string. Now, most of these, this is very hard to do, so you can see this in a full view sort of way. Now, if I wanted to change the force of tension in the string, I could do it by changing this little tuning peg here. So watch what happens as I twist it. You can hear the frequency getting higher as I add tension in the string, and the frequency getting lower as I take tension out of the string. This shows us, if we go back here, that the frequency depends on the tension of the string. And we see that the frequency is directly proportional to the square root of the force of tension in the string. This shows us that as the tension goes up, the frequency will go up. A tighter string has a higher frequency. As the tension goes down, the frequency, the resonance frequency will also go down. This should make some amount of sense to you. If you got a really, really tight string there, a really, really tight string will try to snap back into place way quicker than a really, really loosey-goosey string. And so one that tries to snap back into place way quicker, that's going to have a higher resonance frequency. One that kind of is a little loosey-goosey, it takes its time getting back to its regular place, that one is going to have a lower resonance frequency. The next thing that matters is the thickness. Of the string. On my ukulele here, and this is probably hard to see on this on our visual quality here, but not all of these strings have the same thickness. This one is way less thick than this one. And you can see that they make different notes based on their thicknesses. The ones that are thicker have lower resonance frequencies, and the ones that are thinner have higher resonance frequencies. So we get a proportionality that looks like this. The frequency is inversely proportional to the diameter of the string. And the last thing that matters is, oh yes, the material that the strings are made of, or the density of the string. Now this is very hard to show with my ukulele because all of my ukulele strings are made of nylon. They're all nylon strings. But that's not so with a guitar. If you've ever seen a guitar before, you'll see that there are certain strings that are way denser. They're these thick metallic cords. When you have the thicker metallic cords that have a higher density, they have more mass, which means they have more inertia. So if you say, hey buddy, go ahead and get moving side to side, that thing will go boom, 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 boom. And it won't move side to side very quickly because it has a lot of inertia and it resists acceleration, and it says whipping back and forth really quickly, no thank you. But if you had a string that had a very low density, very little mass, and you said, hey, move back and forth very quickly, it would say, okay, and it would move back and forth very, very quickly with a very little issue. So we see that the frequency is inversely proportional to the square root of the density of the string. That is a little rho right there. Let's see if I can write it a little bit clearer. A little rho. Those are the 4 factors that impact the resonance frequency of a string. And we use these 4 factors when we build string instruments. Most of the time we change the length of the string as we're actually playing it. And these factors, the tension, the thickness, and the density, we use to build the string instrument. Next, let's talk about wind instruments. Wind instruments really only have 1, sometimes 2 factors that determine the frequency of the sound that you'll hear from a wind instrument. Oh, whoops, that's not what I want. I want this thing. It's going very slowly, but I do believe that you can make it if you try. Yes, okay. Okay, here we go. Here I have a little bottle. It's filled with some water. Take some of that water. Dump it out in the sink. Still some water in there. Dump it out in the sink. Take a little more of that water. Dump it out in the sink. You can see that the frequency of the sound that comes out of this bottle depends on one thing. It depends on the length of the column of air that's available to vibrate. When I fill this thing up with water, I make it so that there's less air, there's less length there that thing can vibrate. When I dump out the water, I make it so that that air has more space. There's more air to vibrate. So all that really matters, or I should say what mostly matters for most wind instruments, is the length of the vibrating column. The length of the vibrating column. When we talk about the length, is that how you spell column? Is there an extra U in here? Column. You know what's crazy is I just really don't know super well, but that's why I teach physics and not writing. Okay, here we go. The length of the vibrating column. That's what really matters. Here's why. If you have a nice long column, something like this, a nice long tube, well, a standing wave has to fit in that tube. And a standing wave has to fit in there in a whole number increments. You can't have like a 3/4 of a wavelength. You can have a wavelength, you can have a half a wavelength, you can have 1.5 wavelengths, you can have 2 wavelengths, so you can have multiples of a half, but you can't have 3/4. So let's say that the wave that fits in here is something that looks like this, like that. Notice I've got a 1 wavelength long wave. Well, then if I shorten up the column, so that now the column's only this big, well then the wavelength that fits in there gets much shorter. You know an equation that looks like this. V equals lambda. If I change the length of the column, what I do is I change the wavelength. Here I have a really big wavelength. The speed of the air moving through the column is going to stay pretty much the same here. So if I have a really big wavelength here, if this goes up, then my frequency goes down. So long vibrating columns here, like this one, will create really low frequency sounds. Meanwhile, small columns like this one, you have a very small little wavelength that can fit in the short little tiny tube, and so then you have a much higher frequency as a result. You remember this from your childhood when you played your recorder in elementary school, and the way that you changed the frequency of the note that was being played by the recorder is you used your little pudgy fingers to cover up the little holes on the recorder. What you were basically doing is you're basically lengthening the tube. When you cover up the hole, now the air can't escape through that hole and it has to go down to the next one. You made the tube a little bit longer. When you cover up a lot of holes, well, now you've made the tube really long and the air has to go all the way through before it can escape out the bottom. So you made the wavelength really long. So you made the frequency really low. If you have very few fingers on your recorder and you blow in your recorder, then you'll find that the frequency is much higher because, well, the wave that can fit in there is way, way shorter. The other thing that matters, and students like to ask this question, they say, what about, Miss Wilson, those types of instruments, the types of wind instruments that you use, like the brass instruments, where you actually don't change the length of the column, but instead you change how you blow into the wind instrument. Well, then you're changing V. You're changing the speed of the air that's moving through. If you change the speed of the air that's moving through, but you keep the length the same, the wavelength stays the same, the speed of the air changes, and that changes the frequency. You remember this from your childhood when you took your little recorder and there were a few ways to play it? You could either play it very gently and it would go, ooh, or you could play it very not gently and it would go, ee! And then your mom would say, oh my goodness, can you please not make that sound? Why did you have to play your recorder like that? If you blow the air really, really fast, it gives you a way higher frequency sound. So some instruments rely on changing the speed, but a lot of instruments rely on changing the length of the vibrating column. And that's how we actually change the sound or change the frequency in a wind instrument. So you see that we build instruments like string instruments so that we can change their resonance frequency by changing the length of the string. We build our wind instruments so that we can change their resonance frequency by changing the length of the vibrating column. And then we can play any note that we want to, and we can organize those notes in such a way as to create music. And that, ladies and gentlemen, is a little bit on the physics of music. I hope you have a wonderful rest of your day, and I hope something wonderful and musical happens to you. Bye, good people.